Okay, let's do this. Let's finish skeletal muscle. Okay, so now on part 3, you can see all these purple words and what we are going to cover. So let's go. Okay, types of muscle actions. Based on the picture, what's the definition of each muscle action? Again, normally I would have you guys discuss this and then come up with your answers. We should probably all know this, and we probably are familiar with all these different actions. But let's start with at the bottom. Let's start with eccentric. We talked about eccentric in part 1 of this video, but let's give some more information. So eccentric, the muscle is lengthening, and when that muscle is lengthening, the force of the muscle is less than the force of the resistance. So the resistance, which is external to the body, is greater than the force produced by the muscle. The muscle does exert a maximal force, but the external force is too great to overcome. Or the weight is voluntarily and slowly lowered in a controlled manner. So with eccentric actions, we aren't producing force eccentrically. We are controlling force. That's eccentric. Concentric, let's move to the second one. The force produced by the muscle exceeds the force imposed by the resistance. The muscle can overcome it. Shortening of the sarcomeres, this is explained by the sliding filament theory. So concentric action, when the muscle shortens, when it's the sarcomeres get closer together, that is the sliding filament theory. Yeah, so that's concentric. Concentric is producing force. Force of the muscle is greater than the force of the resistance. And then isometric at the up here, force of the muscle equals force of resistance. So force produced in the muscle is equal to the resistance opposing the movement. There's no visible movement. It's a static force production, but force is developed in an attempt to shorten the muscle. So what's happening here? If force is being produced, but there's no sliding of filaments going on, how is it producing force? Well, the myosin head will attach and detach to the actin in the same spot. There's no pulling of actin toward the M line. So the cross-bridge cycling occurs, but not in the sliding of filaments, just contracting back to, or attaching at the same spot. So there's zero velocity here. Example of isometric actions we probably already know is like a plank or a wall sit. So yeah. Next, this here is basically applying concentric and eccentric actions to weightlifting or exercises or sports or movements. So you're probably going to see this on the next exam. If I give you an exercise, you need to be able to identify where the muscles are or when they're eccentrically contracting or concentrically contracting. So I would normally go around the class and call on people to answer each one of these pictures. So in this first picture here, this is a pull-up or a chin-up. What muscle is shortening? What muscle is undergoing a concentric action? Pectoralis and triceps. All right. What about in, oh, sorry. No, it's not. The biceps. So in a chin-up, the biceps are shortening. In a push-up, the pectoralis and the triceps are shortening. So again, the chin-up in this picture here, bicep shortening. In the push-ups, the pectoralis major and the triceps are shortening. All right, down here, throwing. Pectoralis muscles are shortening in a throwing motion. And then in a kicking, what muscle shortening here? Quadriceps. What about eccentric? Which muscle is stretching? So in the bicep curl, obviously the biceps is going to be stretching as we lower that weight. With the back squat, the quads are lengthening as we move downward. And then in the running motion, what muscle is lengthening? The hamstrings are lengthening as the quads are shortening. So again, you'll probably have 2 questions on the next exam that gives you an exercise, and I'll describe the phase, and you have to basically give what muscle group or area is shortening or lengthening. Okay, so let's describe some terms that describe resistance exercise. Isotonic. So this here is basically describes resistance training with free weights or machines. Iso means same, tonic means tension, because the weight doesn't change during the range of motion. So muscles are able to produce the same force throughout that range of motion. DCER, dynamic constant external resistance, is basically the same thing as isotonic training. And both of those describe your traditional resistance training with free weights or machines. So the resistance provided by the free weight or the machine, it remains constant, because when we pick up a weight, we're not going to change that weight in the middle of a range of motion. We're going to finish the range of motion, and the muscle is going to generate the same force because the resistance stays the same. So yeah, those are the first two terms. They're very similar, and they both describe your traditional resistance training. Isoinertial, similar to isotonic, but it describes movement with changing velocity or changing speed, but still have a constant external resistance during the range of motion. So it's expressing the same inertia in both concentric and eccentric phases of the muscle contraction, facilitating constant resistance and maximal muscle force at every angle. So we see variable velocity means the velocity changes, but there's constant resistance throughout the range of motion. Next is variable resistance, which is this picture down here. This is the resistance that changes over the range of motion. So variable resistance, also called accommodating resistance, uses bands or chains to change the resistance throughout the entire movement. This is in an attempt to match the muscle's force capabilities at different angles of the range of motion. So I'm not going to go into a lot of detail with this, because in your 3322 or 4305, your strength training class, you'll learn a lot more about variable resistance training. But basically, humans are stronger at certain positions of muscle contraction. In this case here, let's say with the bench press, we're weaker kind of at the bottom, and then same thing with back squat, we're weaker at the bottom and we're stronger at the top. So what this does is it changes the resistance, and it actually makes it heavier at the top of the range of motion, but it keeps it the same at the bottom of the range of motion for these two lifts. Because at the top of the range of motion, humans are innately stronger there, and so where humans are able to produce more force. So why not make it heavier where humans are stronger? It actually just allows the muscle to contract maximally throughout the entire range of motion. But again, you can learn more about that in the other class. Last is isokinetic. Isokinetic, so iso is same, kinetic is referring to movement or velocity. But this is usually done on a specialized machine. So this specialized system allows for the speed of movement to be held constant by the device. What this can do is measure torque production at various velocities and joint angles. Torque is just rotational force or force about an axis. This machine is only used in like a rehab or a research setting. But the velocity of the limb's movement is constant. So no matter how hard this girl here kicks out against that lever arm, it's not going to move any faster than what is set by the machine. But the machine can measure her force produced at certain velocities. So yeah, those are your different types of resistance exercise. Let's talk about some different curves here. So the first curve is the force velocity curve. This curve is going to take eccentric, concentric, and isometric actions, and it's going to describe the force of each one of those with a lengthening or shortening velocity. Normally, I would just put this slide up here and let you guys figure out what this is talking about. So maybe try to do that. So pause this video and answer these two questions here. Look at this graph and be able to explain it. Because in a normal setting, I would call on you to tell me what the graph says. So this just helps you learn how to read a graph and then how to explain what the graph basically says. So after you've thought about it, we can already see up here that this demonstrates the influence of changing velocity of movement on how much force we're able to produce. So the speed of the muscle contraction determines the amount of force that can be generated. It depends on the muscle action though. So if we start with concentric, so with the shortening velocity. So the easiest way to do this is think about a bicep curl. So think about a bicep curl and then think about shortening that muscle, shortening that bicep. When we shorten the muscle, the velocity is really quick during that shortening velocity. And with that, we actually produce less force. So force is here on the y-axis. So force decreases during a shortening velocity. Concentric actions actually produce very little force production. We look here at isometric. Isometric actually produces more force than concentric. And I know that's kind of hard to understand at this point, but we'll get there. So isometric, you can see that the force is going to be higher. There's zero velocity though, so we're at zero. So zero velocity, so this is shortening velocity, lengthening velocity, we're at zero. That's where isometric is, and it's higher than where concentric velocity is. And then eccentric up here produces more force than both isometric and concentric. This is the lengthening velocity. So as the muscle lengthens, we're able to produce more force. So it's the greatest amount of force produced is produced by an eccentric action. Next is isometric, and then after that is concentric. Why, you may ask? Why does it happen like this? One explanation is when we're eccentrically lengthening a muscle, think about all the elastic connective tissue that we talked about. That elastic connective tissue supplies more force when it's being stretched rather than when it's being shortened. So the properties of the muscle contribute to that greater force via eccentric action. But if we're still kind of confused here, let's look at this next slide. And yes, this is a video of me. Let's see if these videos actually work. I haven't tried them yet.
Ready? Push!
Okay, did you see how slowly I was moving my leg there? Okay, and then look at this picture, video.
Ready? Push!
You see how quickly? So this is the force velocity curve, but we're only looking concentrically. And we look over here at this graph. So we have velocity. It starts slow and then it gets faster. And then up here is percent maximal torque. So at slower velocities, we actually produce more torque or more force. And at faster velocities, we actually produce less force or less torque. Why is this? Let's watch one more time.
Ready? Push!
So what's happening in my muscle there compared to here?
Ready? Push!
See how fast that was? So the slower time, the more time and the slower velocity allowed for more actin and myosin binding in the muscle. And we learned previously that if there's more actin-myosin interaction, there's more cross-bridging in the muscle, then there's going to be more force production. And here, there's more time for my muscle to form cross-bridges. So that's why these slower velocities over here are going to produce more force. And this is explaining the concentric force velocity curve compared to this one here.
Ready? Push!
Too quick to produce a lot of force. The time is too quick, the velocity is too fast. So you see here the force decreases. Let's talk about training effects on the force velocity curve. And let's first discuss delayed onset muscle soreness. So, we know that muscle soreness, so the soreness that we feel after a workout, let's say 1 day or 2 days after a really hard workout, our muscles are really sore. What is that due to? It's due to mainly eccentric loads. So the eccentric loads, the stretching of the muscles produces all those little micro tears inside the muscles. EIMD, exercise-induced muscle damage, is caused by eccentric actions, and that produces delayed onset muscle soreness. So my question here is, when is it best to focus on concentric muscle actions, and when is it best to focus on eccentric muscle actions? So it's best to focus on concentric muscle actions, like moving really quickly, contracting or shortening the muscle fast, when we want to focus on power production. So when training for muscle power, concentric actions are going to be the best training mechanism. When do we want to focus on eccentric? When we want to train for strength or hypertrophy. So when we focusing on eccentric means slowly performing the eccentric phase. If we're slowly performing the eccentric phase, we're training the muscle to resist more force. And if we're training the muscle to resist more force, that's going to increase our strength. I'm not saying concentric doesn't. Concentric will. So yes, you can still see strength gains with concentric only training, but eccentric will help a lot more with that. And then hypertrophy. If you want the muscle to grow, high eccentric loads is going to be the best way to do that. This curve here, normally I would put this up and I would make y'all discuss this, and you would look at graph A versus graph B, and then you would describe the change that took place. So maybe think about it for a minute, but let's kind of look at it. So this change here, we're going for blue is before training, red is after training. So before training, you can see the force and the velocity that we're able to produce. But the change produced that we see to the red was produced by using high loads at low velocities. So a strength training protocol. So this is a strength training protocol. And over here is low load, high velocity training. This is a power training protocol. So what happened in each of these? So with the strength protocol, we're able to produce greater amounts of force at the same or faster velocities due to greater strength via heavy loads at normal velocities. But the power protocol, low to moderate loads were used using moderate to high velocities. This allows the muscle to produce more force, but at the same velocity, greater power production here. So we can see here we're producing more force, but we're producing it at the same velocity. Over here, we're also producing greater amount of force, but also at a faster velocity. So the goal is to improve the power curve, or improve power across the entire curve, which requires both heavy resistance training and high velocity power training. So we want to shift the curve upward and to the right. So that's how this curve shifts. So if we shift it upward, that means we're producing force faster. So we're able to produce force faster. If we're shifting it to the right, it means we're also stronger too. So upward and to the right, we're stronger, producing more force, and producing force faster. All right, next concept we want to discuss is strength curves. So looking at the amount of force that can be produced over a range of motion. So we have 3 different strength curves that take place on different patterns depending on the biomechanical position of the exercise movement and individual body structure. So the amount of force that can be produced during a movement. First curve we have is an ascending strength curve. This says we're able to produce more force towards the end of the concentric range of motion. Descending, able to produce less force near the end of the concentric, which is the light blue. And then a bell-shaped, which I'll talk about in just a second. So the ascending strength curve, we don't produce very much force when we start shortening the muscle, but once we finish shortening the muscle, we can produce a lot of force. Let me give you an example. Let's think about back squat. So back squat and bench press and deadlift all have an ascending strength curve, meaning that when we start the concentric phase, so not talking about the eccentric phase at all, the concentric phase. When we start the concentric phase, we are not very strong at the very beginning of that, but as we move to like full leg extension or full elbow extension, we can produce more force. Again, it's due to the biomechanical position and the muscular position during contraction. A descending strength curve, we produce less force near the end of the concentric. So it's the opposite. So we're basically weaker at the top or the end. Some examples of this is like upright rows, or reverse flies or flies, and then hamstring curls. So all of those, we're able to start the movement really well, and we're stronger when the muscle begins to shorten. But by the end of the muscle shortening, we're actually able to produce less force. We're not as strong. And then the bell-shaped curve is we're producing more force in the middle of the concentric range of motion. And you can see that here. Highest force production is right in the middle. This basically says we're weaker at the beginning of the range of motion, and we're weaker also at the end of the range of motion, but we're stronger in the middle. And this is due to a mechanical advantage and the lever systems that we have in the body. The only lift here is bicep curls. So if you think about it, when you start a curl, it's really hard to get it up to 90-degree elbow flexion, but once we get it to this point, we're able to produce the most force. But then as we finish the movement, it's a little bit harder to get that full contraction. And let's talk about why these curves exist. But first, we have chapter 4 quiz review. So take a picture of this, pause the video, whatever, and this is what you'll use to prepare for quiz 4, or chapter 4 quiz. But let's finish this lecture because we're almost done. The length-tension relationship. This helps to explain force production capabilities and why we have those strength curves. So what does this relationship tell us? It says that the length of the muscle has a direct influence on the total tension it can generate. So we have active and passive tension. So total tension generated in a muscle is the sum of passive and active tension. Passive tension, due to the elastic elements, but no neural stimulation. So the elastic connective tissue and titin contribute to the stiffness felt. This helps to maintain structural integrity of the muscle and increasing the degree of stretch up to a physiological maximum. So this is passive tension. This is when you put your leg on a desk or on a table and stretch it. You feel tension in the muscle, but it's due to the stretching of the elastic tissue and stretching of titin. It's again when you reach down and touch your toes, like I've asked you to do so many times in this lecture. So when you reach down and touch your toes, that's passive tension. Active tension is generated by the number of actomyosin complexes formed in the by neural stimulus. This is when, okay, now I'm going to ask you, actively contract your bicep. Okay, you're squeezing your bicep. That's active tension compared to passive tension when you just stretch your hamstring. So both those two tensions equal total tension. So the neural activation and just the stretching tension equals total tension that we feel in the muscle. And that's what this bottom picture here shows. But I don't like this picture because it's a little confusing for a lot of people to understand. But let's look at this one here. So this one shows that they kind of both show that passive tension increases with an increase in muscle length. So as we stretch a muscle further, we have greater tension. But active tension will decrease with an increase in muscle length. And this is due to fewer actomyosin complexes formed and less overlap between filaments. So it's kind of what this shows. But this one here shows that the highest amount of tension is when we have an optimal muscle length. So not overly stretched and not too shortened. In the next slide, we're going to talk more about that. But yeah, this slide here just explains different types of tension. Again, with this relationship, total force a muscle produces is related to how much we actually stretch it and how much overlap between actin and myosin. So we already know a lot about actin and myosin, but this picture here, so we have an understretched muscle where actin and myosin are overlapping, or they're overlapping to where they actually can't really interact. So here we have an understretch muscle. Think about flexing your elbow to where your bicep is completely contracted. So yeah, there's some tension there, but there's not optimal tension because there's not enough overlap. Now let's move all the way to a completely overstretch muscle. So if you were to stretch your arm out completely, actin and myosin would actually be too stretched out. And if they're too stretched out, you can see in this picture that they can't interact. And if they can't interact, then we can't have force production. But up here, we have an optimal length. This is partial contraction. So this is like 90-degree elbow flexion. When there's partial contraction, we have optimal overlap between actin and myosin, which means we have optimal force production in the muscle. So this is important to understand force production because we're going to talk about different ranges of motion and different exercises, not specifically in this class anymore, but throughout your journey in kinesiology, you have to understand this relationship to understand movement and to understand force production. All right, next is the force time curve. So this one here helps to visualize force production over different segments of time after stimulation to contract. So normally, I would put this up here and ask you what conclusions about each type of training can be drawn from this graph. So you're basically supposed to tell me what this graph is talking about. So maybe pause the video, look at this graph, and then come up with an explanation and then see if you are correct. Okay, so the ability to produce force quickly after neural stimulation, we know that's an important quality of neuromuscular function. This is important in elderly people when we want to prevent a fall after loss of balance. It's important with athletes when spiking a volleyball or kicking a soccer ball or rapidly dodging an opponent. But we have different types of training here that are going to produce different effects on how we can respond to or produce force quickly. So heavy resistance training, if we look here, the red is our untrained, and heavy resistance training is the green. So this is actually going to increase our force production. We're going to be able to produce more force, but it doesn't change the time it takes to produce that force. So we produce force, but in the same time frame. So we're not any faster than we were. We see here 500 milliseconds. We're not able to produce it at 200 when we just do heavy strength training, because heavy strength training is at low velocities. It's really slow, even though we're producing lots of force. But that's a great improvement. We're getting stronger with heavy strength training. But what about explosive resistance training? So explosive strength or power training, that's going to shift the curve actually this way, shifting it to the left. So what does this mean? This translates to less strength, but also results in, greater strength, translates to greater strength, but also results in reduced time it takes to reach peak force. So we have greater power production and greater RFD, greater rate of force. RFD is rate of force development. So that's what this is basically showing, is that when we do explosive training, we train now in this box right here. What does this box represent? So this 200 millisecond box is talking about sport movements, because most sport-like movements or rapid contractions during exercise take place in about 200 to 300 millisecond time frame. So this is this 200 millisecond time frame. It takes up to 400 or 500 milliseconds to produce maximal force, which is good for producing force slowly, but it actually doesn't help with rapid force production during sports. So this power training component is actually more desirable in a sport, the RFD component, compared to maximal strength, because we want to be able to produce force quickly and be more explosive. But the goal is to shift the force time curve upward and to the left. That's why it's important to do both heavy strength training and explosive power training. Impulse, this here is the area under the force time curve. Impulse is just another characteristic of rapidity, so rapidly producing movement, and it's a product of basically both force and time, so force under, or the area under the force time curve. All right, so that's all your curves that you have to learn. Let's wrap up this lecture talking about adaptation. So we're almost done. We want to talk about how does the muscle adapt. So effects of resistance training, hypertrophy. That just means growth. So hypertrophy means to grow. Anything can grow, but muscle hypertrophy is when we have the synthesis or the growth of actin and myosin within the myofibril. What happens? We have an increased number of myofibrils in the muscle fiber, and that increases the size of the existing fiber. So all fibers appear to hypertrophy when exposed to resistance training, but not all at the same extent. So type 2 fibers will involve an increased rate of MPS, muscle protein synthesis, and type 1 fibers will involve a decreased rate of protein degradation. So that's what happens with training. We also see satellite cells contribute to increases in hypertrophy due to the addition of myonuclei in the muscle fiber, which is required to support increases in cross-sectional area of fibers. So that's kind of the basic of hypertrophy. We see here at the bottom, we see the myofibrils, and then we see a term called sarcoplasmic hypertrophy. That's when the muscle grows in volume, but not due to the addition of myofibrils, just due to the addition of fluid and then other just elements and organelles in the muscle. It's non-functional. We're not stronger with sarcoplasmic, but we are stronger with myofibril. So with more myofibrils, we have more actin and myosin. If we have more actin and myosin, we can produce more cross bridges and produce more force. So myofibril hypertrophy is shown here. Number of myofibrils increases due to increased actin-myosin synthesis. They get larger, and then the entire muscle gets bigger. What about hyperplasia? So this is the increase in the number of muscle fibers via longitudinal splitting, and that's shown here. So we have one fiber, and it shows it just splits in half. Limited data to support the occurrence of hyperplasia in humans. It's only been shown in animal models or with steroid use. So again, it doesn't really occur in humans, only in animal models. But yeah, the hypertrophy and hyperplasia are really neat topics that are discussed more in your strength training class that you'll take in this department if you haven't taken it already. So I kind of stopped there with the hypertrophy and XPhys. Just know it's the growth of the muscle. So it's the growth of the muscle. It increases size of existing fibers due to increased number of myofibrils. So there are different protocols for hypertrophy training that's also discussed in your strength training class. What about effects of endurance training on muscle tissue? So if I was a marathon runner or a triathlete, what would happen to my muscles? So we see here an increase in oxygen delivery to the muscle. What does that do to? So the muscle is getting more oxygen because there's a greater number of capillaries. So more capillaries, and capillaries are just like a capillary bed. That's what you kind of want to think of there, which contributes to greater capillary density. So the density of capillaries is greater. Next is myoglobin. So if there's more myoglobin, we have more oxygen delivery. Myoglobin is a cytoplasmic hemoprotein that reversibly binds oxygen in the cell, and you will learn all about myoglobin in chapter 6. But just know it carries oxygen in the muscle. So if we have more oxygen, we have more ATP. And then we also have enhanced aerobic metabolism with greater number of mitochondria and larger mitochondria, again producing ATP faster. What other adaptations occur? We've kind of already talked about almost everything. We talked about capillaries, myoglobin, mitochondria. Another interesting one is the cross-sectional area of type 1 muscle fibers will decrease with endurance training, which will expedite the rate at which oxygen diffuses into muscle fibers and into the mitochondria, which reduces the distance from the capillary to the mitochondria. So what this is, so basically type 1 fibers shrink. And if the type 1 fibers shrink, it means there's a smaller distance that oxygen has to travel. So we have faster oxygen delivery. And then increased efficiency of aerobic enzymes. So all the enzymes in aerobic metabolism, all of those will speed up and they'll be more efficient. Okay, so what about the effects of endurance training? So this picture here, and I'm not going to spend a lot of time on it, just kind of talks about if we were to perform, let's say, a marathon, or you could even imagine a 10K if a marathon is just like way out of your realm, a 10K or a 5K. When we run like that, we're recruiting about 80% of our motor neuron pool when performing long duration endurance events. And only those fibers that are recruited will adapt. So if I recruit 80% of the muscle fibers in my quadricep, only 80% will experience change. So like the whole muscle doesn't undergo changes. Only the fibers that are recruited will undergo changes. What's desirable is having 80% of your muscle fibers be type 1. So if you want to be a marathon runner, it's desirable to have 80% type 1 fibers in your quadricep and 20% type 2. So that means that the 80% you recruit, that's all type 1, and all of those fibers will continue to adapt. The more type 2 fibers that are recruited, the less efficient your performance becomes because type 2 fibers fatigue out very quickly. So elite runners have mostly type 1 fibers in their rectus femoris needed to perform these demands. So they have about 80% of type 1. But what about the average person? You may already know the answer to this, but the average person has about 50% type 1 and about 50% type 2 across all muscles. That's the average person out there, 50-50. But if you are a marathon runner, you probably have about 80% type 1. Okay, last slide. What does this slide talk about? It talks about what are conclusions from studies on concurrent training. What is concurrent training? That's when we perform endurance and resistance training together. So that's if I was to go run 5 miles in the morning and then do a lower body resistance training workout in the evening. And then I did that for, weeks or months. Concurrent training is where I do a high volume aerobic exercise and resistance training. And those are my workouts. So what happens here? So strength is usually going to be compromised with high volume endurance training. So like if you accumulate 20 to 30 miles every single week, your strength may be lower than it would be if you didn't run that much. Strength kind of endurance running like that, it shrinks those fibers. And if the fibers are smaller, they're not as strong. And so that's one reason that our strength is lower when we start training at high volumes and high intensities aerobically. Power is also compromised. So again, if those muscle fibers decrease, then decrease in size, then they're not able to produce as much force or produce as much force rapidly, which is power. Hypertrophy is also smaller. That's why a lot of distance runners and aerobic exercisers are usually very lean. Yes, they have less body fat, but their muscles have also shrunk because aerobic exercises decreases the muscle hypertrophic response. So it interferes with hypertrophic pathways that increase muscle size. And that's caused by the catabolic nature of aerobic exercise. Aerobic exercise is catabolic because it breaks down the fuel in the muscle fibers to use for energy, but it breaks down that fuel so much that the muscle actually can't grow very well. So hypertrophy is also lower, but VO2 is still very high. So VO2 is not compromised. VO2 max is unaffected by heavy resistance training. So volume of oxygen that you're able to consume, if you're still engaging in endurance training, resistance training will not harm or hurt your VO2. So yeah, that's kind of our results from that. This picture here just shows basically what I just explained, but only talking about strength here. So if I just do aerobic exercise, my strength is going to be very low. If I just do, but then if I do aerobic exercise and strength training, my strength will be higher than it would be if I just did aerobic exercise. But if I did no aerobic exercise and only did strength training, then my strength would be the highest. And that kind of makes sense. But yeah, the kind of the purpose of this slide is to say if you are an aerobic athlete and you really love running or cycling or swimming or whatever you do aerobically, it's probably important to engage in some resistance training, which is going to help build up that strength and build up that power and that muscle size, and make those muscles more efficient. But that's it. That's all I have for chapter 4. So you've probably watched all these videos at this point. You can complete your assignment. You can take your quiz. So good luck with everything in chapter 4, and let me know if you have any questions over anything.